Well, hello there. Today we are talking about my personal favorite. It's an area I've been studying for a very long time, and so I'm delighted to introduce you to circuit and formula complexity. So, areas of circuit complexity and formula complexity are two very exciting and very interesting fields from the theoretical perspective, but they also study something that is very natural. So, basically, circuit complexity studies what circuits can and cannot do, and circuits is what we put in our laptops and phones and computers. So basically everything that right now that has some computational power relies on circuits to perform those computations, right? That means that understanding what we can and cannot do with those very own devices that we are using is vital from the computational perspective. So while algorithms are really nice high-level fields, so like how can we solve problems on this level where we just think that stuff just happens on the computer, right? Like when we perform arithmetic computations, we just say, hey, it happens in basically in a constant time, or in such a swift way, so we don't really think of how long does it take to perform a computation, right? But for example, in a lot of cases, the integer division would be the computational bottleneck. For example, in hashing, they are trying to avoid dividing numbers as much as possible, even by shifting to the hash functions that are just strictly worse than, because they're not used, the computation of them is not using the integer division. Or like why addition of numbers is so much faster on the computer than multiplication of numbers. Again, if you're just trying to add two numbers or multiply two numbers, it doesn't really matter, like your computer will do it in milliseconds. But if you have actually code that runs in a lot of computation, you start getting like the sense that, hey, this block is a lot better than this block, so like addition is a lot better than multiplication, multiplication is a lot better than division, and so on. So understanding how inside of our computer performs arithmetic computation or other computations is vital to improving those blocks, right? So we want our devices to be a lot faster, but also we want to learn what they cannot do, so we can change the design of the device, right? And so whenever we prove a lower bound, it can be an inspiration for a new computational paradigm, right? So it can be a different way. We can say, hey, these ways of computation hit a dead end, so let's consider something else. And sometimes it works. So, all right, let's go through some definitions. So this is a circuit. So what is a circuit? It is a graph that has, it's a directed graph. Some of the edges are marked with a negation sign. And now you have three types of nodes. You have nodes of in degree 0. Those are marked with your variables, right? And we have the nodes with in degree 2. Those are called gates, and they are marked with a logical operation. So in this circuit, I'm using only ands and ors. You can choose a different basis. So this basis is called a U2 basis when we are only allowing ands and ors. You can also allow all possible Boolean operation with two variables. That would be a full basis called a B2. And there are also like a few very exotic bases that you can also implement and see how it works there. But let's stick with this one for a little bit. So we have inner nodes that are marked with ands and ors. We have these outside nodes that are marked with variables, and we have one particular node that has out degree 0 that we just marked. So this arrow to nowhere is not an edge, it's just rather a way to say that this is our output, right? So whenever we plug in some values into those variables, we will get some number here, right? So this circuit computes some logical formula. So let's see an example, right? So suppose I plug in x1 equal to 0, x2 equal to 1, x3 equal to, why do I have x1, x2, x3, x5, and x6? Let's make this x4. Let's say 1, x4 equals to 0, and x5 equals to 0. So what we'll have here then? So this one is 0. This one is also 0. x3 is 1. x2 is 1. x4 is 0. And x5 is 0. Right? So then this one becomes AND of 0 and 1 is 0. OR of 0 and 1 is 1. Then OR of 0 and 1 again is 1. And now we have AND of negated 0, which is 1, and negated 1, which is 0. So this is 0. And now this we have AND of 1 and negated 0, so this is 1. And now we have AND of 0 and 1, so this is 0. So just like this, if we have the values for the variables, we can just plug them in, and then we can go through the circuit and just every time compute the value of the gate. And that's exactly how your devices actually do stuff, right? So those things are made out of wires, and you have your logical elements that are built with some, amazing nanotechnology. And altogether this thing is, it's tiny, microscopic, and put on a chip, and but it is exactly what it is here. So just like this, those things are built into your computer to do stuff. So now the question is, what are things that we can and cannot do with those circuits, right? And it's not always convenient to talk about circuits, so let me introduce another thing, what's called a formula. So the formula is, it is a specific type of a circuit that does not allow things like this. So this is a graph that is, of course, so if I haven't mentioned that, it of course has to be in a cyclic graph. Otherwise, the computation becomes a mess, and it doesn't really, it's not clear what cycles mean. There are a few definitions of circuits with cycles, but we're not going there. It's a mess. But this is just an acyclic graph. So a formula is bringing it one step further and just saying, like, hey, this should be a tree. So an example of a formula would be or of and of negated x1, x2, x1, and x. For example, this is a formula, and it can do stuff. So the question would be, what are things that are, like, right now it might not be clear what we can and cannot do with circuits and formulas. So first of all, basically everything you can do with algorithms you can implement with circuits, and everything you can implement with circuits you can implement with formulas. And if your circuit was of a small depth, then you can implement it efficiently as a formula, where the depth is the longest path from the variable to the output. And by efficiently, I mean the thing we're worried most is the size. So the size and the depth are two main parameters of the efficiency of a circuit or a formula. Again, in terms of computations, the depth corresponds to how fast the thing can perform computations. All right, because this is exactly the depth is exactly the delay between the putting inputs in and having the correct output. If you assume every gate computes stuff in just like one point of time. So yeah, and the size corresponds to how much space your circuit will take, or how much energy it will consume during the execution, or just in general. It's in general the resources that are going into the circuit that are and they matter, right? So for example, any function can be implemented as a formula of small depth and exponential size, and no one is happy about it. So we want things with small depth, we want things with small size, otherwise it's all pointless. All right. What I want to talk now is just to pick a particular class of functions and see what can we do about it. So to see some efficient circuits and formulas for it. All right. So the class I want to talk about is called a threshold function. So threshold theta of x is equal to 1 if and only if sum I from 1 to n of xi is at least theta, and it's 0 if sum from I from 1 to n of xi is less than theta. So this is a rather straightforward function. It just checks if there are many wires and many inputs that are 1. Again, we think of inputs as zeros and ones, which corresponds to true and false in the logical statement. So 1 is for true and 0 is for false. That kind of, and the sum is the regular sum as integers, not as a Boolean values. All right, so let's consider some example. Let's consider theta equals to 1. So the simplest function. Oh, well, actually, you know what? Let's go even further. Let's consider theta equal to 0. So theta equal to 0 is a fantastic example of a function that is independent of the input. Theta equal to 0 means that threshold of x should be 0 if there are less than 0 coordinates equal to 1, which is obviously never going to happen. So we can just create a circuit that would be just a constant 0 that is an output. Yes, if I forgot to mention that, but we can allow the constants in our circuits and formulas. It's almost never useful, but sometimes it could be. And here's an example. Yes, so we have this formula that only is concerned about the outputting. Oh, sorry. We are putting 1. We are putting 1 because yes, I talked about that 0 is never the correct value. So yes, we always are putting 1. And this is just our circuit. It has size 1, depth 1, fantastic. So let's go ahead and think of the example of theta equal to 1. And again, it's not particularly exciting thing. So we just need to verify that there is at least one coordinate of x that is 1, right? All right, so what is the smallest size we can hope for? Well, clearly this function depends on all the coordinates of x. So if it's independent of some coordinate, we can say, hey, let's set all the rest of the coordinates to 0, and now our circuit has no idea what should be the correct answer, because, right? So if the last coordinate that is not in the circuit is 1, the answer should be 1. And if it's 0, the answer should be 0, but circuit has no idea because it doesn't feed on that coordinate. So what I'm trying to say is that we should have all the coordinates, all the variables should be involved in the circuit. And what is the smallest size of the circuit that can have all the variables in it? And variables, right? So the smallest possible size is n-1, because you need to connect them all with in a graph. And yeah, so it's not hard to see that less than n-1 will not be able to connect all the variables. And we can achieve that size, right? So yeah, we can just attach a lot of OR gates into one big tree of size n-1, and then put all the variables as leaves of this tree. So this is a formula. It has n-1 gate, and it has depth about log n. Right, and so it's physically impossible to be of less size or less depth. So this is clearly the best possible formula we can get. But this is very straightforward, right? So okay, let's talk about the real stuff. Theta equals to 2. Oh, that's where the troubles begin. Right? So, what would be the trivial solution? Just as with algorithms, there is often the brute force solution. So it might be a little bit less straightforward, but in this case, it's pretty clear what it is. So sigma or theta equals to 2 means that we want to check that there are at least 2 different coordinates that are set to 1. So one way to do this is to write a circuit like this. So this one here tells me that x1 and x2 are both 1, right? So then this thing would be 1. So this thing gives me, so if this gate is true here, then my function, the whole function is true. So what I do, I just put all possible things like this. So I put all the ends of xi and xj for I not equal to j until I get to xn-1, xn. And then I attach them with a giant OR. Right? So this thing would take my inputs, find a pair, so for every pair it will check if both of those things are 1, and then we take a giant OR of them. So what is the size of it? Well, it's about n square. It's order of n square. Right? So for every pair we are going to have one gate, and then we have to connect all those gates. So in fact it would be something like 2n square minus something small. But yeah, order n square is the right one, which isn't great. N square is pretty bad, but you know. So okay, it will get, and this whole thing will get worse, right? So if I continue this approach, I will fail so miserably. So if I go to the sigma equal 3 with this computational approach, and now I'll have all the triples at the bottom. I'll have n square here, right? So in general, I can have a circuit of size order of n to the theta. And as usually theta is not, so theta could be pretty large, right? So theta could be order of n. So theta, for example, if theta is n over 2, we call this function a majority. So this is an important function. And in this scenario, we will call the size complexity would be n to the n over 2, which is just insanely bad, right? So we need to figure out some other idea that will make this tolerable. All right, so what can we do with continue against sigma equals 2? So this is a really fun idea. What we'll do, we will arrange my variables into a square. Right, so yeah. So I just, this doesn't have any physical implementation in my circuit. This is just, again, this is just the way I'd like to think about my variables, about my coordinates, just that I want to imagine them being in the square shape, right? Okay. So I have k equals to square root of n. I will assume that square root of n is just some integer, so I can do this stuff. Let me draw it a little bigger. So yeah, so we have this matrix filled with just my variables, and what am I now looking at? So what I want to say is that I have my coordinates that are 1 somewhere here. So suppose we can always, like the worst case scenario, there are exactly 2 of them. Like, so I need my formula to be able to deal with a case where there are exactly two of them, and if my formula is reasonable enough, it will be able to handle if there are more coordinates, right, that are 1. So I have two coordinates that are 1, and let's say assume the rest are 0. So when they are in this shape, one of two things can happen, at least one of them. So they're either in different columns, right? Or they could be in different rows. So in this case, they're in different columns. So clearly, if they're in the same row and in the same column, they're just the same thing. And we insist that those are two different variables. So they has to differ either in the column number or in the row number. So the question is, how can we use that? So suppose we know that they are in different columns. What I can do now is, so yeah, let's do this. So first of all, I will construct my circuit. X1, 1. And again, I will now use this double indices system. Again, I still have just n variables, but now I can access them not as just like xi, but xij, which are still the same number of variables, so it doesn't really matter. It's just the cosmetics, right? So x1, 1 or x1, 2, x2, 1 or x3, 1, x4, 1. xk1. So I built this tree out of ORs, and it's just computing the OR of the very first column. So I'm just taking this column and computing OR of the variables in that column. Right? Okay, so that would be my building block. So that would be just like our C1. So C1 is a formula that checks if there are any ones in the first column, right? So now I can have this circuit built out of C1, C2, C3, and so on, CK. So now I have all those things, all those subformulas that each is just a formula of size k that is computing the OR of the particular column. Okay. Now, that is the fun part. What I need to do now is to compute the threshold 2 of those things. So I need to find if there are at least 2 columns that have 1 in them, right? So this is like a recursive call, right? So I don't know how to solve threshold 2 right now, but now I'm calling threshold. I need a threshold 2 not on n variables, but on k variables, where k is again a square root of n. So now this thing is a lot more, tangible than before. So we kind of can recursively do that thing here. All right. So now we need to do the same thing here, but with R1, R2, R3, Rk. So those are just the same as this, but for the rows. So each Ri is just checking the OR of the all the variables in the ith row of that matrix. So, and I'm claiming that now I can just do this. So that would be a circuit that computes the threshold 2, right? So what is happening here? First of all, let's check the size. So the size I'm claiming would be order of n. So we have those guys at the bottom. There are 2k of them. Each of them is of size k. So that would be 2k or 2n in total, right? And then we have those things. Those things are actually pretty small. So the whole size would be of order of n, which is fantastic. Now, so again, the why this thing works is because of this idea that if we have 2 coordinates that are 1, then they would have either different columns, in which case this circuit would be correct, or different rows, in which case this circuit would be correct. Of course, they can differ in both the column coordinate and the row coordinate, in which case both circuits would be correct, but we have an OR, so it's like even more true now, right? So that is all right. So yeah, okay, let's move on. All right, so let us continue. We have solved the case of sigma equals that theta equals 2. So now the question is, what can we do if theta equals to k? So that is, we would need some new approach to that. Like if And we're not even talking about like k equals to 7 or 18. We're talking about k when, let's say, it's again n over 2 would be the good example of it. So what can we do? What can we do about it? Okay. So we have our inputs, and now I want, let's forget about that matrix thing. It was just a one-time thing to never happen again. So now I want to have my inputs just like this, right? And for now, I will also start using not only OR and AND, I will also have an exclusive OR gate. So this one is equal to 1 if and only if exactly one of the inputs is 1. So it is computing the parity of the number of inputs. All right. So what we'll do, we will go through this. So we will go through all those input, all those variables, and we will try to compute the number of inputs, the number of inputs that are equal to 1 up to this point, right? So that's what we are going to do. So I'll take my first 2, and so the first one, I already know that this, if this is 0, the number of ones that I have is 0, and if this is a 1, the number of ones that I have is 1. So now I have a parity of them. So I have, it is 0 if there are 2 of them, or it is 1 if exactly one of them is true. So I can do this and this. So now I have, with those two gates, I have the binary representation of the number of ones so far. All right? Okay. So what do we do next? We need to add this thing. So how do I add x3 to, like, I need to increase this number by 1 if x3 is 1, or I need to keep it like that if it is 0. So basically what we need is the way to add ones to the number. So this gate, again, will just give me the lowest bit, right? Now I need this gate to be what? So this thing will tell me if I have a carry after 1 bit. So if I'm adding 0, 1 plus 1, then this bit will be 0, and this thing will be 1. So this is a carry. This is something that I need to add to this one. So this is my parity of those two. So now this thing gives me the correct first two, the lowest 2 bits of the number of inputs so far. But now, yeah, that's actually enough for the first 3, right? The first 3 cannot be more than 2 bits would be enough to store the amount so far. So, but how do we add the next one, right? Or like the one after that? All right. So now we need to add. Basically, the building block we are looking for is you have a number represented by in its binary form that basically that represents the number of ones up to this point, and then we have this xt plus 1 that we need to add to that number. So let's do that. All right, so here is a number represented by some gates. So this is, let's call it y1, y2, and so on to yk. And we have this additional, so this is the lowest bit, because it's kind of convenient to go from left to right. In fact, I know the numbers are typically written the other way, but for me it would be convenient to say that, hey, this is the lowest bit, this is the highest bit, this is a binary representation of a number of the number of ones up to a certain point in my quest through this array of variables. And we have this additional variable x. So we need to output the same, so we need to output this like z1, z2, zk, and if x is 0, they should be just the same, and if x is 1, then we should output this plus 1. All right? So how do we do that? All right, let's do this. So z1 is easy. We can just say that this is parity and just do that. Okay, how about z2? Well, z2 would be the sum of this thing plus of y2 plus the carry from the previous bit. So that would be parity of this guy and of this guy. All right? So if both of them are 1, then we will have another one going to the next, for the next bit, right? But if at least one of them is 0, then the only thing that is changing is the lowest bit. So this one will still stay intact. So again, we just need to compute this to know the carry. Okay, so how about Z3? Well, kind of the same process, right? So we need to compute the parity of Y3 with the carry from the previous iteration. So the end of those guys. Oh, sorry. The end of those guys. If Y2 was 1 and the carry from the lowest bit was 1, then we will have another carry going even further. So this will go on like this, and so on. So we have so this is a circuit that takes a binary representation of a number and a bit and adding that bit to that number. So now what should we do is just to take, so if we want to compute the number of bits in the whole input, we just need to attach all those things basically on top of each other. So initially all those things are 0, right? So we can just use zeros instead of them. And this is our first bit. It will just go here, it doesn't matter. So this thing calls an adder. So we have x log n zeros, x1, and they're going to the adder. Okay, which outputs again log n bits, which I represent like this. This is kind of, this bunch of wires. And we add x2, and we have another adder, and so on. So eventually, let's say, it will put all of our variables into here, right? So into here. So we will have this bunch of wires that are just the number we are looking for, and then we need to compare it. We need to feed it into block that checks if it is at least k. I will not describe how to make that block. It is not hard, so please use that as an exercise. So that thing will be our circuit to compute threshold k, and it has size n log n, because each adder has just size about log n. So the total size is order of n log n, and that's it. So now we kind of completed our study of the threshold function. So for theta equals 0, it's trivial. For theta equals 1, it's almost trivial. For theta equals 2, there is this super cute non-trivial algorithm. And for larger k, we can do n log n instead of linear, which is still pretty all right. Okay, so now I want to move on to another thing. So as I mentioned here, I was saying that I'm just going to use these exclusive OR gates, which is not a problem in the circuit, because you can simulate the exclusive OR gate with just three and an OR gates, right? So x1 exclusive OR x2. So this thing, well, we need to check that OR of ends x1 not x2, and not x1 x2, right? So instead of having this parity, so this is completely and totally equivalent to x1 x2, right? So in the world of circuits, this is fine, because this can be represented as OR of and sorry, having a brain freeze of x1 x2 x2 x1, right? So this is our thing. So again, it has just 2 inputs, 1 output, 3 gates inside instead of 1. So it has triple the size, which usually doesn't really matter that much, right? So that's like times 3 is not what we're usually concerned about. But in the world of formulas, when we want those things to be trees, we are switching a block with just 2 inputs with a block with 4 different inputs. So if those things were not variables but some sub-formulas, then this doubles the size of those sub-formulas, of the formula. So now I use those sub-formulas twice. I mean, again, this is just like another times 2, which shouldn't be a problem, but it is. It is, because if I then have a parity right here, right, I will split this thing again into 4 things instead of 2. So if you do that repeatedly, you can get a horrible mess out of what you are trying to do. So yeah, in terms of formulas, it's basis with just ends and ors and basis with added parity are very different things. So in this case, let us just consider the complexity of computing the parity of the input. But now we are not allowed to use a parity gate, otherwise it would be kind of silly of us, right? So we want to compute x1 exclusive or x2 exclusive or up to exclusive or xn. And we want to build a formula out of ands and ors. Fantastic. How can we do that? So again, I think of my inputs as a string of zeros and ones, and I need to compute parity of that string. So I will try to, like this divide and conquer approach. What I'll do, I'll split it in half. And I'll say, hey, how about I'll compute the parity of the left half, and then I compute the parity of the right half. And that is equivalent to knowing x1 parity xn over 2, and then I would know xn over 2 plus 1 xn. So out of those two, how can I get my answer? So I can just, so I already know those. So this is my P1 and this is my P2. What I need is just P1 parity P2, which is not available as a gate to me, so I do it as just as we talked about it, or of and of P1 and not P2, so and then not P1 and P2. And once again, I apologize, I don't know what's wrong with me, but that should be and rather than or. Where again, P1 and P2 are those things. And so this is my P, like P0, right? And then what we'll do, we can just recursively compute this, like P1, by splitting it into P3 and P4, right? And do that. And if you do that whole thing to the end until you get just one bit, which is a parity of itself, you will end up with a formula that is just this ands, or of ands, of or of ands, and so on, and then you have variables underneath, and so the depth would be, let's see, so every round, every iteration, we split our inputs in half. So so the depth is, so we need log n rounds to reach our inputs. Every round costs us the depth of 2. So that would be 2 log n. And 2 log n in depth translates into size equals to n squared. And we kind of already seen something like that. And that is what Karchman-Wigderson games are coming into play. So we already talked during the last lecture about the Karchman-Wigderson game with the relevant definition. So in that game we had Alice have an input with parity 0 and Bob has an input with parity 1, and they need to find a bit of a difference. So it turns out that the protocol for communication protocol for this Karchman-Wigderson game is equivalent to the formula computing the function. that defines Kachner-Regression game. Moreover, those they're not just like have equivalent parameters. So, I remind you that for Kachner-Regression game we indeed build a protocol with 2 log n depth, and we have 2 log n depth here. So not only the parameters are equal, we have the correspondence between the protocol, communication protocol for Kachner-Regression game, and the formula. So we can translate from one language to another. This is 2 different models that looks completely different, and it turns out that those are just 2 different languages to talk about one thing. So there are no difference between Kachner-Regression games and formulas for functions. So yeah. I hope you enjoyed it, and we will talk about decision trees the next time. I'll see you then.